Hello and welcome to Full Paper Session 6. I'm your chair, Daniel Archambault. In this session, we have a series of 4 papers on machine learning and explainable AI. And it should be very interesting to hear what all of these authors have to say. Just as a reminder, you can type in your questions into the Discord channel or onto the YouTube live chat. After the video presentations, we will have a Q&A where we can answer those questions for you. But without further delay, I will quickly introduce our first paper. So our first paper is iQUANT, Interactive Quantitative Investment Using Sparse Regression Factors. And thank you very much.
Hi everyone, this is Xuanwu from Innovation Venture China. Today I will present our work iQUANT, Interactive Quantitative Investment Using Sparse Regression Factors here. This is a joint work with Carnegie Mellon University, Institute of Software, Chinese Academy of Science, the Hong Kong University of Science and Technology, and Singapore Management University. From 1970 to 1990, there are more and more investment research reveal that small cap stocks tend to outperform than the large cap stocks. At first, the result turned out to be the skills of different portfolio managers. With the development of factor research, it became clear that stocks with certain characteristics could explain a lot of differences in diverse portfolios' return. The first factor model, three-factor model, was proposed by Farmer and French in 1992. The model assumed that the return of stocks or portfolio could be explained by 3 factors, which are market risk, market capitalization, and book-to-market ratio. In summary, the 3-factor model is a new capital asset pricing model, which we can use to explain why the small cap stocks had better performance than those large cap stocks. Then the research has been extended to have a clear explanation of excess return alpha. More and more research papers have been published for new powerful factor discovery. However, many of these factors do not pan out. In many cases, they turn out to be a repackaging of the original factors. Same factor may perform differently in different stocks. So, how to evaluate factors and find out the ones are worth pursuing is the key issue. The models mentioned above are mainly used in long-term investment, but more and more investors tend to pursue the profits from short-term investment. Here is the difference between long-term and short-term investment. The characteristics of factor investment in short-term investment means that the investors will bear more pressure and they need to repeat tedious calculation and statistics evaluation in a huge factor space. This raises a question of how to help them improve the efficiency of finding effective factors quickly and efficiently. In recent years, some feature selection models have been applied to the field of factor investment. Although the investment experience and skills of portfolio managers are beneficial, there are no tools that can combine human experience and algorithm output to improve the efficiency. In response to this problem, we have proposed a virtual analytics solution. These virtual analytics techniques can combine human knowledge and algorithm models to accelerate the process of knowledge discovery, thereby improving the efficiency of finding effective factors. The goal of this work is to assist the investor in formulating better factor investment strategy based on historical market data through virtual analytics, so that they can get more insight of their portfolio. Starting from actual industrial scenarios, we propose interactive factor selection or interactive feature selection, which is a general research problem in VisEvol community. According to related work survey, we found that the existing work could not solve the problems properly in our scenario. Here we list 3 related works. You can refer the draft for more detail. The first one is infuse. The infuse design a glyph with feature importance, but the temporal pattern of factor or feature is omitted. As for the regression explorer, they build one model for the whole dataset, but in our scenario, each portfolio needs one model to evaluate. After serious interviews with financial institutions, quantitative works, and fund managers, we summarize 5 requirements and 4 tasks here. There are 4 parts in the workflow: data storage layer, application layer, user interface, and user. First, A. User select target universe of securities, time range, and initial factor model. Secondly, B. The system fetch historical stock and factor data to train the factor selection model and apply the model output to simulate backtesting. Thirdly, CDE. The virtual analytic system shows model output backtesting result and other metrics to evaluate. Fourth, F. The user interactively adjusts the factors and the back-end model will recompute correspondingly. In this way, the workflow will reach the step B again. We implemented iQUANT by using China A-shares stock market data. We first downloaded the historical stock data from Kucher, which is an open free data source. The dimension of data is rich and well formatted. Over 28 years and 3,600 securities are collected. The second database is Factor Library. We refer the research from People's Bank of China School of Finance, PBCSF, which is a Chinese official financial institution. The research defines 56 factors in China A-shares market and divided them into 6 categories. They are momentum, profit, growth, value, liquidity, and transaction friction. We calculate all these 56 factors by two-share data. As for the factor investment model, we choose the cross-sectional regression model in iQUANT. Y is the stock return vector. W is the factor return vector. X is a pre-processed factor exposure vector. B is bias, which is the excess return alpha. Epsilon is the error. As shown in the figure, the data used in regression model is a cross-section of stock and factor. Also, we use MLE to estimate the weight vector of all factors. In iQUANT, the number of factors is 56. D is transaction period, which is 21 trading days in every month. T is training days, which is 252 trading days in every year. So the training set length of individual stock is T divided D, which is 12. For the scenario of a certain sector or an index component, the number of stocks in the target security set is small. The number of factors is equivalent to the number of training samples, which may lead to serious overfitting problem. Thus, we introduce a sparse regression model to achieve feature selection. Lambda controls sparsity. This work mainly applies to basic sparse regression models: Lasso model when alpha is 1, and the elastic network model when alpha is 0.5. The corresponding visualization will be set according to the model output, which mainly included the factor weight W, the factor contribution Wx, and the factor value. Here is the interface of iQUANT, which contains 6 different views with inter-view interactions to fulfill the analyst's tasks. I will introduce every view from the left to the right. The first one is control panel. You can add different stocks into the target candidates, like the shopping cart. Then select the time range and model type. When you click Draw, the backend will run regression model on selected stocks and return the results to visualize. The second is factor view. We designed to show the temporal patterns of all factors in different months. Every circle is a factor. The color encodes its category. The radius is the contribution or weight or value of each factor. You can change the metrics above. We display factors based on their categories with fixed order. You can click on one specific factor to track its change. In order to avoid the virtual clutter caused by the intersection of lines when displaying multiple factors, we respectively display the positive and negative contribution of each factor, where the factor with positive weight is placed above the x-axis. It is connected by a red line, while the negative weight is placed below the x-axis and connected by a green line. In the process of designing this view, we also implemented and compared many other different visualization designs and show in the following figure, such as circle packing, tree map, stream graph. But after investigation and communication with domain users, we finally denied those designs owing to the space efficiency and learning cost. The next one is stock view, which is a summary of factor performance on every individual stock. The x-axis is timeline and the y-axis is the average stock price change ratio. We align two factor glyphs in every time unit to display top 5 contribution factors in every month. The height of inner bar is stock price change ratio, while the y means model prediction error. And for the factor glyph, 6 sectors represent 6 factors categories. The area of sector is factor contribution. Top 5 factors are encoded with its belonging color, and the left factors are colored in gray. When there is more than one factor in one sector, a Voronoi map is used to display. In this way, we can observe which color took the majority part in every month to analyze their temporal pattern. When users click one factor in the factor glyph, a line would link this factor in different months to track its change. This is factor list, which is a general observation of all factors' contribution on all stocks during the selected time period. Each row is a category. For each factor, upper part is a positive contribution, while lower part is its negative contribution. When you click one bar, its corresponding line will be highlighted in previous 2 views, factor view and stock view. The stock return view is designed to show stock returns in order to compare and select from the candidate stocks. The green line is individual stocks return, and the blue line is the return of sector index, which is average return. When you select one stock, the line will be highlighted in red, and all selected stocks are chosen in the portfolio. The last view is backtesting view. An industrial standard backtesting function is provided to evaluate portfolio performance. The blue line is market return. The green line is previous portfolio's return. When you interactively adjust the portfolio and recompute the backtesting, the current portfolio's return line is encoded in red. Okay, and for the evaluation, we respectively conducted quantitatively and qualitatively evaluation. The qualitatively analysis here is divided in 2 parts, case study and user feedback. Quantitatively analysis is a user experiment to verify the effectiveness of iQUANT. Owing to the limited time, we choose to introduce 2 case studies and user experiment results in our presentation. In 2015, the market experienced a spike with the maximum index climbing as high as 60% in the first 6 months and turned down in the second half of the year. It's thus an appropriate scenario to test whether iQUANT can improve factor investment even in rapidly changing market. In order to construct the portfolio, the manager would like to select both valuable factors and a set of stocks which behave in a similar stable and effective way. The manager first studied the chemical sector, which had a similar trend to the market in 2015. He clicked on each important factor, and identify candidate stocks in the stock view. Lag return, which had a moderate overall contribution to stock returns of the sector, and the contribution was stable on several individual stocks. As shown in the figure, the selected 3 stocks share similar patterns on lag return. When the stock price started to rise again from September, the contribution of lag return reversed to negative and stayed for a few months. It is found in the red of the figure that 5 stocks, the red lines, sharing this pattern on this factor, receive excess return above the market average, the blue line. The performance in backtesting also surpassed the market average. When the manager went back to check the factors, he found another one, STDDVOL, had similar pattern and the lag return on the selected stocks. After applying the 2 factors together, the stock returns were recomputed and updated in the stock return view. One stock appeared to receive less return after adding the second factor, so the manager adjusted the stocks from 5 to 4. The final portfolio of 2 factors and 4 stocks turned out to be better than the single factor portfolio in the backtesting performance. The second case study is CSI 500 Index Analysis. The CSI 500 is capitalization-weighted stock market index. It has been regarded as the Chinese S&P 500 index. The index uses 500 most representative stocks in the Shanghai and Shenzhen stock market and sample, and most of the stocks are small-cap companies. This kind of company is characterized by strong volatility in the stock price, easily affected by macroeconomic policy and market environment. Here, we applied elastic net model during 214 January to 217 December. The figure shows the change of the factor's contribution over time. We can clearly see that the green color dominates. The green color stands for the transaction friction factor. This corresponds to the factor that the stock price of CSI 500 are with highly volatility. The following figures show the factor performance on the thermal power sector and the real estate sector. We can find that the dominant factors of these 2 sectors are different. The thermal power sector is mainly took up by transaction friction factor, which is represented by the green color, and the real estate sector is growth factor, represented by the blue color. We can observe different market or sector styles from iQUANT. In the user experiment, we designed questions correspond well with system tasks and invited 16 industrial quantitative works. We compare iQUANT with online industrial platform, and the results reveal the correctness and efficiency are improved compared with current standard product. In conclusion, iQUANT provides factor selection model based on sparse regression model and a subsequent interactive factor refinement. In terms of visualization, we propose multiple coordinates views and design a factor glyph based on the Voronoi map. Besides, an interactive virtual analytics framework is provided in iQUANT. Users can continually refine factors and stocks to optimize investment strategy in a virtual analyst closed loop. Here is all my presentation, and we are focusing on the virtual analytics of financial data. If you have any interest or concern, please feel free to contact with us. Thanks for your listening.
Hello, and we're back. We're here with Xuanwu, and we're here to answer some of your questions. So we have a bunch of people on the Discord saying this nice presentation and that sort of thing. A little bit of a comment on your slide 17. Skewed labels make the bar appear if they're slightly skewed as well. But anyways, I'm wondering if there are further questions. Please type them in YouTube Live or type them in the Discord and we can ask our authors. Lots of nice presentations. It's all good to hear. So lots of people think the presentation's nice.
Thanks.
So I have a question. You did a bunch of, you did a bunch of expert interviews in your qualitative study, 16 of them, right?
Mm-hmm.
So with most of those interviews, were your experts mainly confirming things that they knew about their data set, or did they make new discoveries? What were the main findings there in your qualitative interviews?
Yes, and I think the main objective of the domain expert or users is to optimize or find a portfolio, and our tools is to help them evaluate the factor of their portfolio. So previously they may use different charts or different individual visualization to compare, but use our iQUANT, it can enhance the efficiency of optimizing the portfolio, and the efficiency and the correctness is improved. Yes.
Oh, okay. So it's more about optimizing their portfolio. So given a current state of the market and that sort of stuff, they want to optimize return. Is that basically what they're trying to
Yeah,
do?
that's it. And another point is that they have their initial factor pool or stock pool, and they can use the interaction to select or to optimize or construct the portfolio in a very less than 1 minute to evaluate.
Okay, very good, very good. So let's see here. We got a couple of questions coming through.
Mm-hmm.
Maybe we just wait a second here. I was about to launch into a question, but let's see here. They might be actually very long questions. Oh, we got one here. We got one from Roy Ruddle.
Mm-hmm.
So the visualizations in your system are quite rich and encode many variables. Given the significant differences in sites found, what can you tell us about which elements of the viz were used and how they could be simplified?
Oh, I think the major, like the overwhelming visualization is the number of views. But for each views, we design it as simple as possible because the learning curve for the domain expert or financial experts, and they get familiar with the line chart or bar chart. But you can regard it as every view, it is as simple as possible, but we keep it in the loop. Like we want to like the users evaluate or finish the work, the tasks within the loop, like the 4 wheels in the middle and left and the right. Yeah.
Okay, so you would say that those are the two main visualizations, yes?
Yes.
Okay. And we got another question from Richard Broth. There are factor models that have hundreds of factors. How will your system scale?
Yeah, that's a basic scalability problem. And right now we implement our system with 56 factors. And I know in the industrial or in the real scenario, they may have hundreds of factors, but right now we use two hierarchical, like the factors and the category. So we use like 6 category to encode. And yes, I think the scalability is a good question, but the thing is that we assume that if the users want to import their factor pool into iQuant, they may have a pre-selection, like optimize their factors into like 1 to under 100, I think. Yeah.
Okay. So the idea would be to use what the computer is good for to reduce the number of factors, high computation stuff, and then you have a smaller number of factors that are available for visualization.
Yes. Yeah.
Okay. Another question from Roy, following on from my first question, but many views, increase cognitive load. How do we reduce the views or integrate them?
I think like the factor view or factor list and stock view, they are different aggregation or summarization of the factor information. So you can select or you can construct your portfolio based on only one view, but we design three into different perspectives. So I think if we omit the views, we can like the factor view, factor list, and stock view, and I think that the views can help you in more information. Yeah, but you can judge or you can make the decision based on only one views.
Okay, thank you. Thank you, Xuanwu. Very interesting questions. Lots of interesting questions here. I'd like to encourage people to continue discussion on the Discord, and we can answer some of the questions there. But we would like to thank Xuanwu, and then we can move over to our next presentation.
Okay.
Hello again. We are now proceeding to our next paper presentation, which is entitled VisEvol, Visual Analytics to Support Hyperparameter Search Through Evolutionary Optimization. Thank you very much, and take it away.
Hello everyone, my name is Angelos Chatzimparmpas. I'm a PhD student at Linnaeus University, Sweden, and I'm here to present our paper entitled VisEvol, Visual Analytics to Support Hyperparameter Search Through Evolutionary Optimization. This work is a collaboration with my colleagues Rafael Martins, Kostiantyn Kucher, and Andreas Kerren from Linnaeus and Linköping universities. We will start with a brief discussion of the motivation for our work and the related research that we found. Then we present the details with regard to the functionalities of the system, and at the same time we describe the first use case with the goal of selecting a composition of models with specific hyperparameters for the creation of a majority voting ensemble using healthcare data. Afterwards, I will briefly mention the application of our system for the task of classifying molecules as biodegradable or non-biodegradable. The results show improvement in the process of evolutionary hyperparameter optimization and improvement in the performance based on multiple validation metrics. Then we have the presentation of qualitative results of expert interviews we performed, which showed promising results. And finally, I will finish with a discussion of limitations and future work opportunities we identified. Let's start with a short definition of what is evolutionary hyperparameter optimization. It is a hyperparameter optimization approach that creates an initial population of random hyperparameters, evaluates hyperparameters using a validation metric, ranks the hyperparameters by their relative fitness, replaces the worst performing hyperparameter tables through crossover and mutation, and finally repeats steps 2 to 4 until algorithmic performance is reached or no longer improving. But how do crossover and mutation works in VisEvol? In this example, we observe two different algorithms, k-nearest neighbors and logistic regression, with 2 and 4 models respectively. This projection provides the user with an overview of the hyperparameter space. We can now select high-performing clusters and proceed with deciding which models to include in our voting ensemble. With crossover, random pairs of underperforming models originating from the same algorithm are picked and their hyperparameters are fused with the goal of creating a better model. As a result, internal regions of the solution space are further explored, and better local optima are investigated. On the other hand, mutation randomly generates new values for the hyperparameters to substitute old values. It facilitates scanning for external regions of the solution space to discover additional local optima. Although the synergy of combining crossover and mutation techniques can be beneficial in finding distinctive local optima that generalize to a better result in the end, which models should crossover and mutate, and to what extent, is one question that emerges. This challenge stems from the enormous space of available solutions, with several algorithms to choose from, and instantiations of these algorithms using different hyperparameters, in other words, models, that lead to the exploration of diverse regions of the extensive hyperparameter space. To exacerbate this problem even further, those machine learning models perform differently according to various validation metrics. There are several existing visual analytics approaches, tools and systems developed for sequential-based, bandit-based, and population-based approaches, but not evolutionary optimization. ATM-SEER implements a multi-granularity visualization for model selection and hyperparameter tuning. It is a visualization tool coupled with a backend framework called ATM that allows the users to interact with the middle steps of an AutoML process and control them by adjusting the search space dynamically during execution time. In contrast to VisEvol, it only supports a single performance measurement, and the output is a single optimized model. HyperTuner is an interactive visual analytics system that enables hyperparameter search by using a multi-class confusion matrix for summarizing the predictions and setting user-defined ranges for multiple validation metrics to filter out and evaluate the hyperparameters. Users can intervene in the running procedure to anchor a few hyperparameters and modify others. However, this could be hard to generalize for more than one algorithm at the same time. In our case, we combine the power of diverse algorithms, with one of them being actually a neural network. From prior works, we described 5 analytical requirements in the paper that helped us to design a coherent visual analytic workflow for hyperparameter search using evolutionary optimization. VisEvol comprises the same workflow, which I'm just going to present. Choose suitable validation metrics for the dataset, which are then used for validation during the entire process. In the next exploration phase, compare and choose specific machine learning algorithms for the ensemble and then proceed with their particular instantiations, in other words, the models. During the detailed examination phase, zoom in into interesting clusters already explored in the previous phase, and focus on indications that confirm either their approval in the ensemble or their need for transformation through the evolutionary process. Control the evolutionary process by setting the number of models that will be used for crossover and mutation in each algorithm, and compare the performances of the best so far identified ensemble against the active majority voting ensemble. This is an iterative process with a final composition of the most performant and most diverse majority voting ensemble. The generated knowledge regarding hyperparameters is fed back to the user, whose trust in the results increases and his stops when his or her expectations are met. The video demonstration presents a use case based on the heart disease dataset. It showcases the main components of the system and the real-world application. VisEvol uses multiple validation metrics which can be combined into one single measurement for increasing trust in the results. In our case, as our dataset contains balanced healthcare data, we choose validation metrics such as accuracy, precision, recall, and F1 score. We initialize our random search for hyperparameter tuples with a default 100 models for each algorithm, since it offers a balance between computational time and solution space exploration. Finally, for comparison reasons with another work, we choose a tenfold cross-validation strategy. The workflow of the system is divided into 3 main parts: exploration of models and their hyperparameters, management of the evolutionary optimization process, and evolution analysis and composition of the ensemble. Our visual analytics tool allows the users to pick the best and most diverse models for the ensemble from different areas in the projection. Using the other coordinated views, the user can compare the selected models against all models and act accordingly. Let's see VisEvol in action again. The hyperparameter space view shows a UMA projection of all models generated by random search at this phase, but also new hyperparameters from the crossover and mutation stages. The models with a similar performance across different metrics are positioned closer to each other. As we focus on performant models, we choose to zoom in and explore impactful clusters of points. First, we select the cluster on the left side. In the B-swarm plot, the y-axis summarizes the overall performance of models, and the x-axis sorts the models into 5 distinct bins based on the algorithm. Despite the small deviation in pixels shown in the bar chart below, we observe in the B-swarm plot that this group of points contains highly performant random forest models, which are represented in black color. Moreover, in the bin plot that illustrates the performance of the individual models for each validation metric, we identify that accuracy, recall, and F1 score are reaching among the highest values on average. A similar analysis is performed for the 4 remaining clusters in order to spot diverse in terms of performance models. A further step towards such a discovery is supported by the grid-based visualization. This view is split into 2 areas for the healthy and diseased classes. For each class, the x-axis represents the mean and per-algorithmic performance for each data instance. The instances are sorted according to the mean for every class performance, in other words, the first bin. Furthermore, the y-axis showcases the performance of all models compared to the user selection. KNN and MLP models appear to perform better in hard-to-classify instances compared to the remaining algorithms. If we use a lasso for choosing the top middle cluster, we can check the difference in predictive power from -100% to 100%, color encoded with diverging purple to green colors. KNN and MLP models are absent from this cluster, and there is a slight improvement in the central region of instances for both classes. Hence, we decide to skip the addition of models from this investigated cluster to the ensemble of voters. Next, we finalize our selection of models for the majority voting ensemble and send the leftover models for crossover and mutation with the default settings. Users are able to conduct similarity-based analysis relevant to the algorithm's predictions, which are the initial indications for tuning crossover and mutation of stage 1. The various perspectives that multiple views have to offer for several algorithms further support those prior analyses. We provide explicit visual feedback from stage 1 of crossover and mutation towards stage 2 for users to select appropriate numbers for model optimization and test their hypothesis. In summary, VisEvol displays both successful and underperforming paths for every crossover and mutation stage. At this stage, the hyperparameter space updates with new hyperparameter tuples. The crossover process randomly picks pairs of models originating from the same algorithm and blends their hyperparameters. The mutation process follows the same principles, but instead it computes new values for the primary hyperparameter of each algorithm and injects these values in the hyperparameter set of randomly selected models. The same color map as in the grid-based view is used for highlighting the difference in number of over or underperforming newly generated models. The feedback from stage 0 to stage 1 in the Sankey diagram allows us to fine-tune the last stage. In case we hover over the saturated purple line, we conclude that 24 models are below the worst KNN model explored so far with random search. This means that mutation was bad for the KNN algorithm in our experiment. Moreover, as we already mentioned, KNN and MLP models are equivalent in comparison with the other algorithms. Thus, we decrease the default number of crossover and mutation of models towards stage 2. This way of thinking repeats for all the algorithms until we converge to a final evolutionary optimization plan. After a series of explorative analysis of clusters, we reach to a consensus about which models are going to be added in the majority voting ensemble. A comparison between the currently active ensemble against the optimal solution found until that point in time is possible via our tool. Overall, it assists the extraction of a competitive and effective ensemble. And now, the final part of the video demo. At this point, we recheck the Sankey diagram and understand that almost no new models seem to be more powerful, except for a very few cases of KNN, LR, and MLP models. Consequently, we avoid moving extra models from the hyperparameter space to the ensemble's visual embedding. The majority voting ensemble contains all models from the preceding stages and has the same properties as the hyperparameter space projection. As we want to favor the global structure and investigate further which combinations of models lead to better predictive results, thus we adopt the MDS method. Then we iteratively narrow down to the important clusters. For example, the random forest model on the top right corner is the most powerful overall. The horizontal bar chart supports this indication because it enables the comparison between the actively explored ensemble against the best ensemble we encountered so far. Another MLP model, which was generated through the crossover procedure, is better only for the diseased class if we take a look at the grid-based visual representation. Two more grad-B models are mostly good predictors for the healthy class. In general, it is essential to try to maintain a balance for the independent variable in a binary classification problem. With that in mind, we consider that composing an ensemble of equal voters consisting of those four models will actually improve the predictive performance. Indeed, the final majority voting ensemble is more powerful and rather simplistic than any other combination ever examined before, because it accounts not only pure performance but also diversity. In this use case, we concentrate on the improvement of the predictive outcome for a binary classification problem that utilizes the QSAR by degradation dataset. To verify whether our findings were reliable, we applied the resulting majority voting ensemble to the same test and external validation datasets as Mansouri and others. For the test data, the reported accuracy was approximately 87%. In our case, we reached 89% for accuracy with the final voting ensemble. Additionally, as an extra validation, we checked the results for the additional external dataset. Using our approach, we managed to achieve the same accuracy as before, 89%, compared to 83% reported by Mansouri and others. For more details, we refer the interested listener to our paper. 3 machine learning experts evaluated VisEvol in individual 1-hour interview sessions. The feedback was related to the following aspects: workflow, visualization and interaction, limitations. All in all, the feedback was remarkably positive and encouraging with the choices we took during the development of VisEvol. For instance, 2 out of the 3 experts commented that the workflow of VisEvol is well designed. Although the third expert expected a more linear workflow, she agreed that the combined views are better positioned at the top, with the interactive projections in the middle and the shared views at the bottom. In another example, 2 out of the 3 experts were delighted by the possibilities of the visual exploration of the hyperparameter space. 1 out of them was particularly enthusiastic about the grid-based view and stated that it is a game changer for finding performant and diverse models. The excessive computational time required for producing new hyperparameters along with ensemble learning methods can be problematic. Despite that, one possible improvement for VisEvol is to utilize parallel processing on powerful cloud servers. Moreover, we believe that the advancements in high-performance hardware and progressive visual analytics and data science workflows will be beneficial for VisEvol. Another open issue is the avoidance of hyperparameter tuning per se. The goal of the tool is not to explore or bring insights about the individual sets of hyperparameters of the models or algorithms, but instead we focus on the search for new, powerful models and implicitly store their hyperparameters. We could also allow the user to specify the hyperparameters range at every state and test alternative mutation strategies. Checking combinations of evolutionary optimization with a crossover and mutation process applied to the best performing models is another limitation. All in all, these limitations constitute possible directions for future work. That was it from my side. Thank you all for your attention, and remember to visit the links below for accessing the paper, testing the tool online, watching the demonstration video, and tweaking the code of VisEvol.
Hello, and we're here with Angelos to answer your questions. There's currently lots of applause going on in the Discord, so nice presentation, nice presentation. More nice presentations and lots of applause, or sometimes it's viewed as hand washing, but it's applause, I guess. All right. So, Angelos, you have a nice system that essentially presents an overview of a bunch of these models and similarly performing ones, correct?
Yeah, exactly.
Okay, so another way of looking at this visualization problem is looking for nearby models. So instead of having an overall, I want more models like that. Have you thought about this problem and ways of extending your system to do some of these more local operations?
Yeah, thank you for the question. Actually, one of the strategies that we used was that we want to cross over and mutate the kind of bad models in a way. So we want to select a couple of good ones, then we want to make them, to be preserved and survive, and then we want to make the worst models become better. So what you're saying is exactly another strategy of evolutionary hyperparameter optimization, which actually makes a lot of sense, and it's something that we want to work in the future. But actually, we faced a couple of problems with that. The problem is that when you're selecting a region of a few models, then it is very hard if you're falling more or less in a loop, because you cannot find you cannot cross over models. Because if you have too little models, like three, four models, that you try to mix their hyperparameters, then it's not possible if you at the same time want unique models, because we always create unique models in this case. Of course, if we remove the limitations of uniqueness, then you can achieve exactly the same, and it's something that we want to try in the future.
Okay, thanks. So as a reminder, guys, you can type questions in the Discord and on the YouTube chat. So if you guys have questions, then please definitely type those in. Okay, so maybe as a second question, sort of going off of this overview idea, and you mentioned you want the good models to perform better and the not so good models also to perform better. As you're doing this steering, that's great, because you can steer you can steer the models in certain direction. Are you worried a little bit about steering into local minima? How do you avoid that? Any thoughts on that?
Yeah, that's very interesting, actually. So yeah, while you're steering the model as the user, you might, as you said, fall into these local kind of optimas, or not global ones. So this is why I think the power actually of this evolutionary optimization is that you're doing a crossover. So you're looking for kind of internal regions in a way, and then you have also the external regions which are explored via the mutation. So you have the mutation to search random areas in the space of solutions. So this is maybe one of the kind of benefits of using this hyperparameter approach.
I see. So you're saying that the mutation operator is going to help alleviate some of these concerns, and so those will pop up on the screen, and then you can combine them with other models there. Okay. More nice presentations and all of that. Well, it looks like we're getting close to the end of the question time. So I'd like to thank Angelos again, and we will shortly proceed to our next presentation.
Thank you.
Hey, we're back, and now we're proceeding to our third speaker of the session. So our third speaker of the session will be speaking about learning contextualized user preferences for co-adaptance guidance in mixed initiative topic model refinement. Thank you very much, and on with the presentation.
Hi everybody, my name is Fabian Sperle and welcome to the talk on learning contextualized user preferences for co-adaptive guidance in mixed initiative topic model refinement. Work that I've done together with my colleagues Hannah Hauptmann, Daniel Keim and Menatala El-Assadi at the University of Konstanz. Topic modeling is a process in which we try to assign documents from a collection to a set of topics that we identify in the process. Usually that's not a straightforward task though, especially not if we want to integrate the user's domain knowledge and their preferences into the final result. In the past few years there's been lots of visual analytics research on how to best perform this integration, and the result are now lots of different operations that can be used at different times. In this work we wanted to support the user in picking the right operation at the right moment in time regarding their analysis context. We built on our previous work that allowed users to interact with representations of their topic model to refine it, and previous work that introduced quality metrics as a good way of supporting user in their topic model refinement process. In this work now, we introduce single objective guidance agents as a new way of generating guidance in model optimization tasks. Each agent offers only one specific model optimization, and consequently a task becomes identifying unique contexts in which it can make its suggestions. Users close the loop by providing relevance feedback and teaching their agents whether the suggestions were actually useful or not. In this talk, I want to introduce those agents in more detail and tell you how and when they learn to provide guidance based on the temporal development of quality metrics. I'll also share qualitative and quantitative feedback from our evaluation that we performed on the topic model refinement system. Before we go into all of those details though, let's take one step back and look at the incremental hierarchical topic model that we use. IHTM is a simple, intelligible and transparent model. It iteratively inserts documents into the tree-like structure that you see on the left. Without going into all of the algorithm details now, let's just look at how this works in the system. On the right hand side we have the document log where documents appear one after the other to be inserted into the model. To its left, the rotated icicle plot represents the current model state. We color the topics in this icicle by obtaining bird embeddings for their keyword descriptors that we then project onto a 2D color map using UMap. Consequently, the color of the topics represents their semantics and similar topics have similar colors. Finally, the Sankey diagram on the left shows the temporal development as well as keyword changes and color shifts of topics. The icicle plot offers refinement functionality via drag and drop, which is great for smaller optimizations, but it's not the most efficient way to optimize larger models. To that end, we rely on 6 optimization strategies from our previous work that all make predictable changes to the IHTM. We allow users to combine and split topics, reinsert small ones, and remove topic chains. These chains are narrow and deep subtrees that can sometimes appear as artifacts of the IHTM process. Further, users can reinsert outlier topics and also reinsert the worst ones according to some quality metrics. Each of those strategies provides the goal for one of the single objective guidance agents that will only make suggestions of that specific type in appropriate contexts. In the interface, we represent the agents as cards below the Sankey and icicle plots. Before we see them in action in a second, let's take a closer look at their goals. First, the agents want to support the users by making suggestions, providing a preview of the suggested model state, and also verbalizing their changes that they're suggesting. They also explain their reasoning by stating their confidence and uncertainty, as well as the most influential decision rules from their classifier. Most importantly though, the agents learn from user feedback through the buttons in the top left corner of each agent card. As each agent relies on only one specific optimization strategy, its goal becomes to identify those situations in which their guidance is useful and in which ones it's not. And to that end, all of the agents train independent classifiers that are independent of the classifiers of all other agents. Here we see the system in action. Documents are inserted one by one, appearing first in the document log and then in the model icicle, and we get agent suggestions as they become relevant in their contexts. We can inspect those suggestions in detail using comparison views and also have access to the underlying documents before we accept or reject any of the suggestions. Once we do that, the stream continues and more documents are inserted until we get more suggestions. Unfortunately, we don't have the time to go into too much detail about the system design and the interactions here, but you can find a lot more details in the paper or by exploring our demo at topicmodelguidance.linguist.io. In the remainder of this talk, I want to instead focus on the single objective guidance agents as a technique to generate guidance. Here's a very broad overview of the workflow that these agents afford. They take the analysis context into consideration and then provide a binary decision on guidance that the user then gives relevance feedback to. We'll go into detail on all of those steps, and in particular we'll see how we vectorize the analysis context so that we can use it as an input to the agent's classifier, how we store the relevance feedback, how we ensure maximum learning from the few limited interactions that we have during a visual analytics session, and ultimately how the rule-based classifier works. Let's start with the vectorization. To generate the context vectors, we observe the metric development over time and split the time series into distinct windows. In our implementation, we use a window size of 1, which means that we generate a new window after each document that has been added. To summarize the metric development over time, we represent all of those windows by one of the 7 basic shapes that you can see here. These shapes encode whether the metrics went up or down in a given window and provide a simple representation that's comparable across different metrics. We repeat this step for all of the windows and across all of the metrics that we consider, and then we can finally construct the analysis context vectors as the concatenation of all of those metric shapes. Each of those vectors now describes situations in which different optimizations might sense. In the topic model example, consider a decrease in coherence and separation, and that can easily be mitigated by splitting one larger topic into 2 smaller ones. Now that we know how the input to an agent's classifier looks like, let's assume that they do decide to provide guidance in that situation, and then the user either accepts or rejects that as relevance feedback. This feedback is stored as acceptance and rejection counters for all of the contexts. However, here one issue arises: the more metrics we use and the higher dimensional our context vector becomes, the more unique these context vectors are. As a result, it becomes less and less likely that we ever see them again in our analysis, and also it becomes less likely that we utilize the learning that we have just made. To mitigate this issue, we introduce partial context vectors with reduced dimensionality. Essentially, they are the power set of each context vector. Any feedback that we collect for a context vector, we then apply to all of its partial context vectors as well. And as those partial contexts appear more frequently, they capture broader feedback and they capture it much more quickly. This broader feedback is useful to form guidance decisions when no feedback has yet been recorded for more specific context vectors, as we'll see now. Agents use a rule-based classifier to decide whether to provide guidance in a context or not, and consider not only context vectors, but also all of their partial contexts. For all of that information, they determine the weight as the ratio between how often the suggestion in a given context has been accepted over the total number of suggestions that have been made in that context. They then sum up all of those weights. And if the sum is above 0, they provide guidance, and if it's below 0, they don't. We chose this rule-based classifier as it can be incrementally updated as new relevance feedback becomes available, and it's easy to explain to the users in terms of the decision rules used. However, in principle, our technique could work with any other classification algorithm as well. Before we come to the evaluation, one last detail about the classifier. The addition of the partial context means that we capture more broad feedback more quickly, but it also means that we capture a lot of duplicate information. Consider this example. These two vectors here have, among many others, this shared partial context, which has even more shorter partial contexts. To remove duplicate information now, we count how often each of those partial contexts appears. For all contexts that appear equally often, we only use the longest, most specific one in the classification now. As a result, we only rely on the most specific context vectors that are available and only fall back onto the broader, more general ones whenever that is necessary. This balance allows the agents to quickly map out the entire context vector space with initial feedback that they can then incrementally refine over time as more specific feedback for more specific context vectors becomes available. To evaluate our technique, we rely on a multifaceted human-centered evaluation. First, we performed a pair analytic study with 4 PhD students from computational linguistics and political science to evaluate the system usability and also the participants' preconceptions toward guidance. Then, using the same 4 participants plus 4 new ones that had not seen the system before, we performed a topic ranking task to evaluate the validity of the learned rules and the timing of the provided guidance. Finally, we also perform an investigation into rule transferability between datasets. In the pair analytic study, the participants explored and refined the second 2012 presidential election debate between Barack Obama and Mitt Romney. They generally found the guidance to be well-timed and helpful. However, some were also concerned about the agents over-exploiting the feedback that they had gotten, creating sort of echo chambers or bubbles that could potentially be difficult to escape from. At the same time, the participants were willing to spend significant amounts of time on training their agents in return for better guidance in the future. This pair analytic study confirms the general effectiveness of our agents for mixed initiative topic model refinement. Beyond that, we rely on quantitative experiments to evaluate some specifics in more detail. In the topic ranking experiment, we were interested in whether the agents could be used to automate the model refinement once they had been sufficiently trained. To test that, we trained them on the same dataset used in the pair analytic study, and after training, automatically applied them by accepting all suggestions on the training dataset and also on a second presidential debate from the same year. Our results show that the automated refinement is received better by study participants than the baseline model in both of the cases. That's in contrast to our previous work where we found that automated refinement of topic models towards quality metrics actually worsened the performance significantly. While this experiment shows that the agents learn meaningful rules, we also wanted to know whether these rules are useful for providing well-timed guidance. In the second experiment, we provided the participants with modeling situations represented as screenshots of the system and let them choose which of the split, combine or reinsert worst agents, or none of them, they would have chosen in that context. In general, the participants were very certain in their decisions and the agents predicted those decisions with an accuracy of 35%. However, when looking at the data more closely, we noticed that most of the participants did not actually distinguish between the split and reinsert worst agents, as they have similar effects on the model. They remove topics that were unwanted. If we remove that distinction in the data analysis, we find that our agents reach a 52% accuracy. Finally, we wanted to investigate rule transferability to figure out whether the agents had only picked up on some spurious outliers or whether they actually learned meaningful rules that could be transferred to new datasets. The very brief summary is that the agents consider similar numbers of contexts during both the training and automation runs, and that the confident rules that receive more consistent feedback during training are also the ones that are more likely to be transferred to new and unseen data sets. In particular for this experiment, but also for all of the other evaluations, more details and justifications are in the paper. To summarize, we have introduced single objective guidance agents as a new technique for contextualized guidance generation and shown that they learn generalizable and transferable rules in our instantiation for topic model refinement. Thanks for your attention and happy to take any questions.
Hello, and we are back, and we're here now with Fabian after his exciting presentation, and we're getting lots of applause and great work and congratulations in the Discord. Now I'm just reminding people, if you have questions and the like, you can type them into the Discord, or you can type them into YouTube Live, and we can forward them on to Fabian so that we can get more information on his work. Okay, so we have a question from Sylvia. Nice talk. Guidance is very important. When timing to provide guidance is important, how do you assess the timing is correct beyond asking the subjects?
We did two different evaluations of the timing. First, in our qualitative expert study that we ran with these 4 PhD students from computational linguistics and political science. At 3 points in time, we asked them whether they found the guidance to be helpful and also whether they found it well timed. And there we saw that there was a slight increase in, after the agents were learning, in the timing, that the how well the participants rated the timing of those tasks. And the second evaluation that we did was with the other participants in the second study phase that you saw in the talk, where we had these 9 modeling situations in which the agents had provided guidance during the qualitative study, for which we then took screenshots of the modeling scenarios and provided them to the participants together with the choice of whether they would have chosen that agent or a different agent in that given situation. However, both of these, they're 2 different approaches, but they still require that we ask the participants whether they found it helpful or not. In contrast to what we saw in the previous talk, where we have clear metrics and we can do things like AutoML and optimize towards higher accuracy and higher precision, higher recall, the goal of our system was to enable personalization of the modeling results, right? So there is no clear way, at least not yet, not that I know of, how we can automate this task without getting the participants' feedback. So we didn't evaluate guidance timing without actually asking participants.
Okay, so thank you. We have another question here from Davide. So did it happen that the participants rejected the guidance because they wanted to try on their own before accepting the suggestions?
No, that did not happen in the study. Instead, they were typically happy that they finally got guidance. We had a few moments where there were similar suggestions by similar agents, which made it a bit more difficult for the participants to choose between, similar suggestions that were made, but they never rejected guidance because they wanted to do it on their own. Instead, what we found was that they were actually very keen on spending time to really investigate these suggestions, to provide good feedback and train their agents so they could get better and better guidance suggestions in the future rather than doing things themselves.
Okay. Very good. While we're waiting for some of the questions, in your qualitative, you had a qualitative user study where you asked participants that were they familiar with the data sets beforehand? And if they were, how much do you know, how much do you figure it's from the visualization corresponding to what they're seeing or their prior knowledge of the data or the problem?
None of them were familiar with that particular data set, which is why we chose one that is so old, because most of the participants had analyzed the newer ones from 2016, for example, in the presidential debate. They all had experience with analyzing discourse, with analyzing debates, but none had experience or none had ever analyzed that very specific second presidential debate in 2012.
Okay, thank you.
But of course, they knew what to expect, that they would talk about taxes, that they would talk about the economy and so on. They had their expectations of how the final model should look like, but they, like I said, didn't explore that data set in detail before.
Okay, so yeah, they had a little bit of a mental model going in, but that particular data set could still supply some surprises.
Exactly.
So we have Sylvia again. Did you explore different degrees of guidance according to Synodus's definition? So different forms of guidance. That one's kind of hard to understand. And then Natalia said at the same time, a good idea, train guidance agents to provide better guidance. Can you speak on that topic or?
Yes. So to answer Sylvia's question, no, we did not explore different guidance degrees. All of the guidance that we do provide is, I would say, somewhere between orienting and directing guidance. One of the design goals of the system was to never interrupt the analysts in their analysis. So we have this stream that's constantly running and we have new documents that we are adding over time. And these agents and their cards, they pop up at the bottom of the screen whenever the agent thinks that it has a meaningful suggestion, but that does not automatically stop the stream. And the agents also never request feedback by like blocking the rest of the interface. Yeah, so I would say it's probably it fits best into orienting guidance.
Okay. And the second question about good idea training guidance to provide better guidance.
Yeah, I mean that was the main goal, is that in many of the guidance applications that we typically have, we start from the perspective that we want to figure out that we know of in a situation that the user might need guidance, and then we try to figure out which guidance to show to them. And in this paper, we essentially take the inverse approach by first defining through those agents what guidance operations are available, and then letting all of the agents figure out through relevance feedback when they should provide that guidance. And we implemented and evaluated that now for topic modeling with our 6 topic model quality metrics. But we think and we hope that this could really become a generalizable technique that you can also apply to different model optimization tasks that you have. Of course, this mostly makes sense when you want to have personalized results, right? And you want to enable your users to go beyond optimizing precision recall, like we have in topic modeling, for example, where we frequently find that political scientists have different expectations than computational linguists, for example. And the advantage of those agents, hopefully advantage, at least in our paper, it was one, is that those rules that they learn, those contexts in which to provide the suggestions, turned out to really be transferable, at least between similar data sets. So we could envision a future in which you have your set of agents that you train on one data set, and then you just take them to the next task that you want to solve, and you keep refining them there.
Very, very good. We have lots of very nice comments in the chat. You should go in the Discord. You should go read some of those. But we're currently running a little bit short on time. So I'd like to thank Fabian again. Thank you very much for answering our questions.
Thank you.
And we will head to the next paper. Hello and welcome back for our final paper of the session. This paper is titled A Visual Designer of Layer-Wise Relevance Propagation Models. So let's play the video and have a look at this work.
The title of this work is A Visual Designer of Layer-Wise Relevance Propagation Models. We thank all co-authors and also thanks all anonymous reviewers. Deep learning models, especially the deep neural network, have achieved a great success in many applications. However, the computational kernel of such deep learning models is mostly like a black box to the users. There is a lack of techniques to open this black box so that user would understand and can explain why the output is generated. For example, they will help to answer the questions about is the prediction result reliable? Is there bias in the output? In particular, interpretability and explainability for deep learning models are needed in different applications. This talk is about our work based on layer-wise relevance propagation models, LRP models. It is a good model to explain a classifier's prediction. It mostly works on image configuration neural networks such as CNNs. In particular, it uses some computational methods to backpropagate the relevance of the particular predicted class, go back to the input image, and provide a relevance score for individual pixels in the output. So it will generate a relevance map for a selected class and visualize as a heat map to show to the people. For example, in this graph, we show the input image and throw into this CNN neural network. Based on this LRP backpropagation, we finally visualize it as relevance map, so it can be shown on this heat map view. We select the castle class in the prediction, so this LRP model will tell people this red pixel have a high positive relevance, and this high blue value will have a high negative relevance to this predicted class castle. In particular, LRP is a method developed by many computer vision scientists, which are used in many applications. However, these LRP models require a trial and error process in the applications, because LRP propagate this relevance score from output to input image with different ways and different rules. These LRP backpropagation rules are developed by many scientists in different ways. There exists a set of rules, a popular one, such as what they call LRP gamma, LRP alpha beta, LRP epsilon, and many more. In real application, this rule needs to be tied to different images. Moreover, these multiple rules may be applied to different segments of one neural network. And for each of these rules, there are a set of parameters to be defined. So you can imagine it will be a very time-consuming process for the user to decide which rule should they use, which should be applied to each segment of the neural network, and how can they set up these parameters. So there is no optimal solution that exists, so they need a lot of work in the trial and error process. This is an exploration process with user experiences needed to find the good solution and understand the deep learning model output. Therefore, we develop a visualization software. We call it Visual LRP Designers, which is a visual LRP model designer to provide an integrated computational framework of multiple LRP rules. Based on that, we propose a visual workflow for LRP configuration. It allows the user to visually set up LRP rules and parameters on different segments. And after they set up multiple LRP models, we have them to perform this visual model analysis with two popular ways. One is the neuron aberration, another one is pixel flippings. We will show the example later. So in summary, this LRP designer is visual designers so that user can easily study LRP and use LRP. First, there is a lot of LRP rules with different formulas. So to make this visual design easy, we make a unified formula as shown here. And the multiple LRP rules can be represented by this formula with different size of the parameters. In here, we're not gonna go into the details. After that, we also help users to define these composite LRPs so that they can split CNN layers into multiple segments and easily adjust these segments. So they can easily apply and define different rules over these segments and compare their relevant results.
So, with the LRP Designer interface, we allow users to set up LRP models, such as assign and change segments with the parameters. And also, we provide a software-based visual manager, so that they can use it for saving and loading present models. The most helpful part is we provide visual interface so that they can immediately check the prediction scores, relevance heat map, computational results for different predicted classes and at different layers. Now we will show the demo of this VisLRP Designer interface.
Here, in the manager, 4 models are created to study popular LRP rules. These models are LRP Epsilon, LRP Gamma, LRP Alpha 1 Beta 0, and LRP Alpha 2 Beta 1. These models are designed based on the pre-trained neural network of VGG16, and the prediction list with top scores and classes are also corresponding to this neural network. Now, we continue to create a new model and customize its alpha and beta values based on this neural network. We change the default setting to make it as LRP Alpha 3 and Beta 2. Users can get guides on how to set the parameter values by hovering on the question marks. The LRP rules will automatically be changed with parameter settings. Then, users can run this configuration and save it if it is good. We also can load models from files. To configure with a different architecture neural network, such as ResNet34, users can select this in drop-down, and get the LRP output with neural network layers and the top prediction list of this neural network. Now, users can select one image glass of wine to compare the relevance heat maps in the model comparison view. These newly imported LRP models are based on ResNet34 architecture. Finally, the user can also change to a different color spectrum of relevance heat map for a better results checking.
After users set up these different LRP models, we allow them to compare these models with different rules and different parameters. In this example of comparison, the target class is the red wine. The total relevance score of this class is used in the back propagation. 5 different LRP rules highlighting the important pixels mostly surrounding the red wine object at the center of the output heat map. We also can find the trend that the irrelevant pixel in the background also suppressed from the configuration 3 to configuration 1, or from configuration 3 to configuration 5. Notice that in the LRP computation, the negative weight in the configuration 1 and the configuration 5 are highly kept, but the negative weight are totally filtered out in the configuration 3. So the contribution of the negative weight, which can distinguish the different classes, can be found through this comparison. This insight also can be checked and confirmed by comparing the same LRP rules and the target classes in the different neural network architectures. Users also can build composite LRP models.
In this example, 4 composite LRP models have been created with multiple segments based on this neural network. Users can follow up the existing model to improve and create the 5th model. The segment on the ruler can be redefined at CNN layer range by dragging the border, and the rules of the segments also can be updated by setting in the configuration panel. User can add a new segment for this new model. After setting, users can test it by clicking a target class for this new model to check the result.
After setting composite LRP models, we can have one more example of comparison. In the first row, we study the class bound about the relevance heat map in this input image. In the second row, we study the class aux with the same input images and models. Then we can see the effect of different rules in different segments, such as different layer ranges for the same 2 rules to form 2 different models in the red box. And a rule LRP epsilon is further added into 2 new composite models to suppress noise in the green box. And another customized LRP rule is added to further improve the relevance distribution on the related class object in the pink box. We also can find some of these LRP models are failed to identify the important or relevant pixels related to the corresponding classes, but some of them can highlight the correct pixels for the class object, such as a barn, house, as well as ox. So users can learn these configurations of composite LRP rules are good to apply in such images. Also, they can find which rules are suitable to apply to a particular depth of layers in a neural network for more general application. In this visual LRP designer, we also provide a capability to analyze models with two ways. The first one is the pixel flipping. After computing LRP relevance scores of input images related to a special class, we can flip either high or maybe low relevance pixels to 0, so that we can check the changes obviously in the prediction. Thus, we can have a better understanding about why this model gives us a special predictive result, and is that model works okay or not. So, pixel flipping is used to explain and improve these models. For example, this one shows that the same image we flipped some of the pixel, which is highlighted in yellow, and then it will generate a new result instead of its original predicted classes. Here is the demo of pixel flipping.
Based on the output of one LRP model, we brush over the image or the relevance heat map. Then, the new prediction result is computed and visualized for comparison with the result of the original image. Here, the new top class of prediction is water buffalo after flipping the pixels, which is changed from the original top class barn. Users can also create a new flipping row and brush a different part on the image for comparison.
Another way for model analysis goes to neurons instead of just the output result. It is neuron ablation, which is the very popular method in the analysis of neural network. That is, we interactively remove specific neurons based on the LRP scores on those neurons, so that we can evaluate how the prediction result change with these particular neurons. It is also an effective method for model explanation and improvement in neuron levels. Here is the demo for neural ablation.
Users can also load a new image and perform neuron ablation based on relevance study for the same model. The layer 2 is selected and then the neuron points are visualized over 3 charts. They are the distributions of positive relevance scores, negative relevance scores, and CNN activation scores. By selecting top neurons in positive relevance, we can further check these neurons for details in the neuron matrices. We could also observe the relevance, heat maps, and activation heat maps of these neurons. If some neurons do not relate to the class after checking their heat maps, users can also click on individual cell to remove or add them back from the selection. Finally, the new CNN prediction results are shown here after the selected neurons are removed from computation. In this example, the new top class has become prison house instead of the street sign.
In conclusion, this VisLRP designer provides a good and easy, effective design of LRP models in deep learning explanation. Users can explore multiple models with relevance data visualization together with the integrated visual analysis tool for evaluation. In future, we will do more studies on the LRP parameter space. Also, we will have more technique options to be added, such as functions of layers fusion for the batch normalization, and bias switching. Different approaches like attribute discriminative LRP and visual debugging tool. We will also apply to voice and language learning models. Thank you.
Oh, hello and
Hello.
welcome to the question and answer session. Xingyi is with us to speak about this wonderful work. I hope
Yeah.
you're well. The talk is so exciting. It generated 2 questions in the Discord before you're even done. So I will read the first one. So this one's from Thomas Schultz. Very interesting work at NeurIPS 2018. Adebayo et al. Proposed sanity checks for saliency maps. What do you think? What do you think about those sanity checks? Do you think it might make sense to integrate them into your system? Could they be useful for pruning the apparently quite large parameter space?
Yes. So the parameter space is about the neuron the neuron parameters, and the LRP method is trying to use the prediction score to backpropagate through the neural network and project to the input space. So based on the output, those relevance score on each pixel in the input space, we can evaluate how the performance of this LRP model, and at the same time, this relevance score also will be used to highlight the important neurons in the model in the neural space. So then, according to the output of the relevance score distribution on the images, the output space, we also can know whether this distribution of the relevance score in the parameter space, in the model parameter space, is well distributed or not. And then if it's good, the output is good, and then we can know the important neurons highlighted by the relevance score in the model should be also good, and then we can prune the neuron according to the neuron distribution, relevance score in the neuron distribution. So that is one of our method, which is to the second method to evaluate how well the model is LRP model is set, and then if its model is good, we can filter out the important neurons. So I think that is one way to test to our models, and also on the other hand, we can use this way to prune the neural parameters.
I see. Okay. Thanks. I noticed the next 2 questions and my question in my notebook are kind of similar. So my question in my notebook was basically this is applied to images. What about other data sets such as text? And I'm going to zip up that question with the 2 others. So Stefan der Elsen says, thanks for the presentation. Nice work. These methods work great for CNNs, so we can see the relevance in the image and the heat map and interpret them visually. Have you thought about how it would work for generic multivariate data? And Natalia Adrianko suggests, what about applying it to text and interpreting by human? So you have a nice system. What about other data sets like multivariate data or text?
Yes. That's a good question. So actually, for the application of the LRP method, there is it's doable on the text to understand which word maybe contribute importantly, and I think that for currently our system hasn't integrated for those kind of model, which is for a recurrent neural network. But certainly it's doable for the LRP to apply it to do the text analysis, and that is also one of our work to do in the future. Yeah. Did I have another question I may missed?
No, I think you did a good job of all those questions. It was text and also other multivariate data.
Okay.
So I think we have an idea. Unfortunately, we're running out of time, and there is also some pretty good questions on the Discord. So if you guys could go into the Discord and answer some of those questions, I think we can continue the discussion there. So thank you very much for your presentation, and I will shortly close the session.
Thank you.
Yeah.
And everyone, that concludes our session. We had 4 very interesting papers today with some very interesting questions and discussions. As a reminder, one of the key things with virtual conferences is you can continue the discussion on the Discord. So this channel will be open and you guys can ask questions of our authors and that sort of things on the Discord. I would like to start by thanking our 4 papers and all of the contributors on those papers. This was a very interesting session that generated lots of interesting discussion. Thank you very much for your contributions to EuroVis, and it was very fun chairing this session. Also, I would like to thank the EuroVis tech team and everybody who's making this work behind the scenes. This has been going flawlessly. I really, really like how you've been running the sessions, the questions, and all of the activities that we have been undertaking at EuroVis this year. So unfortunately, we're out of time. Thank you very much for listening in. And with that, I'm going to bring this session to a close, but please don't forget that you can continue the discussion on the Discord. Thank you very much. Daniel Archambault signing off.